Next we will talk about another content called ICMP. Control Message Protocol. This is an important protocol at the network layer. But it is not actually encapsulated at the network layer. Now the network layer uses. More is the encapsulation of IPv4. 2-layer encapsulation. 3-layer packaging. Logically speaking, it should be a 4-layer package. But ICMP is the same as ARP. The top layer is ICMP. There is no transport layer and application layer behind. Is encapsulated on top of the IP header. This is 3 floors. This is the second floor. This is ICMP. So we often call ICMP a layer 3.5 protocol. Because it works on top of the overall 3 layers. It is encapsulated in this location. The back is the same as ARP. Nothing at all. It is also a special message form. Then the ICMP we talked about today. What exactly does it do? When we transfer data in the future, the first thing to know is that for the ICMP message, the transmission of data pays attention to the back and forth of data. Let me explain what this means. The host sends a message to the peer. The peer needs to reply with a message. This is what we said. Data goes back and forth. Represents that the two hosts are connected. There is no error in passing between them. So now this message, able to reach each other. And the other party also allows to return data packets to host A. Then once host A receives the data packet from the other party, it knows that it is now connected to the peer. Before the host wants to send a message to the other party, first ping them to see if they are connected. If you pass, send it later. It's like in real life when you're talking to someone. You call him first. He promised. You continue the conversation. If you are far apart, or separated by several people, you suddenly start talking to him. He wasn't there when you spoke. Or you call him. It didn't hear either. So ignore you. Then you won't keep talking. You have to make sure he is listening to you. And he can hear what you say. There is no problem. You can transfer again. It is used for error detection. It comes in 2 forms. One is ping. One is traceroute. Let's start with this bug report. ICMP has 2 forms. The ping we have learned so far is one of ICMP. And traceroute is also a. So let's talk about this ping first. Sometimes when we go to ping an address, you will find I am within a certain period of time. No response from the other party. This is one of the forms. We call it request timeout. Let me show you. For example, I'm going to ping an address now. 2.2.2.2. It's definitely not working. So it will show request timed out. That is, if I go to ping an address, no reply from the other party within the unit time. Called request timeout. So what does this request timeout mean? Let me give you a brief explanation. For example, now this is PC1. This is PC2. Passed through a lot of equipment. Because in the end, it goes through many devices of the operator. A route that executes. Then in the process of forwarding. As long as this PC1 sends out the data packet, send to the next device. However, due to various reasons, resulted in no reply. This is called request timeout. So there are various reasons that may be a problem here. Or something is wrong here. Or here. Here. Including when the subsequent data packet is returned. There is a problem with any node. Didn't go back to this device anyway. Are called request timeouts. For host A, The request timed out. Then there is another situation. The second is called destination host unreachable. For example, I will ping another address. I'll check the current address first. Look at my network segment. I go to ping 192.168.1.222. Here is an unreachable destination host. If I perform the corresponding ping command, I get a response in my command line. Unreachable destination host. My order was not sent. Or was blocked. It has many possibilities. I give a simple example. Now this is PC1. This is the first router. Through many routers. Finally arrived at an address on the far end. If now, my message is going to the first router. When doing the first retweet, there is a problem. Here it will show that the target host cannot be accessed. Because the data cannot reach the next device. Devices are sentient. It knows this is not sent out. This is called host unreachable. Usually, there are two kinds of. The first is that PC1 did not send data. For example, it has no appearance of ARP. No way to encapsulate. Suppose it is going to visit this 1.222. But actually, this network does not have this 1.22. It is equivalent to not having this host at all. Can't request its MAC. There is no way to encapsulate. So there is no way to send. It means that the data has not been sent out. The second is, we may do a data interception on the router side. That is, this data needs to access an address on the back end. But I'm cutting the flow here. No access. So this data packet cannot be sent out. Then here will prompt. Unable to reach destination host. Here's what the two error messages suggest. Everyone should know this. Okay. Let's move on. This is the format of an ICMP packet. I'll show you. This is a two-layer encapsulation. This is the E2 I wrote for you. Three-layer encapsulation IP header is packaged at this location. In addition to the verification of the second layer. The follow-up. There is no fourth floor. Only one ICMP. There are types in it. Code. Checksum. ICMP is specifically a content. Well, actually for us. Different messages represent different content. Here are its specific details. Then let's take a look at type and code. Generally speaking. Encapsulation based on IP header. We call it encapsulation based on 3 layers. ARP is above the second layer. This is the second floor. The 2-layer package is E2. We are called encapsulation based on the second layer. Working on the second layer is called encapsulation based on the second layer. This is a layer 2.5 protocol. ICMP is encapsulation after the second and third layers. We call encapsulation based on the network layer. Also known as working above the network layer. Is a layer 3.5 protocol. But strictly speaking, it does not belong to the transport layer. If you have to ask which floor it belongs to in the second, third, and fourth floors, it belongs to 3 layers. Because there is a port after the transport layer, we are going to control. It cannot provide the port of layer 4. So it definitely doesn't belong to the 4th floor. It can only be said that it is a 3-story. Because it cannot realize the functions of the 4 layers. Let's briefly talk about these unreachable. Host unreachable. Network unreachable. Actually these two. I just told you. The internet is not all smooth sailing. Suppose my data is sent. This is the sender. This is the destination. This data. To the next device. then whatever the reason behind. As a result, this data cannot be returned. This is called network unreachable. The host is unreachable. The device may now be doing some kind of policy. It doesn't let others ping it. Or, I may have sent the data now, since the destination host may not be online. Also known as host unreachable. Or, I am now going to ping this address. Doesn't exist at all. Then I can't do data encapsulation. This is also known as host unreachable. Let's focus on these two. Protocol unreachable. Port unreachable. Because I didn't explain these two. Agreement unreachable means that when I send a data now, the destination has been reached from the local. Then I will now communicate accordingly. Based on the network layer. Up there are different agreements. For example, TCP and UDP at the transport layer. If what I want to access now is the TCP protocol. But now the other party has not opened this agreement. So now I have no way to allow the other party to access. That is, my protocol accesses the other party's protocol. If the other party does not open this agreement now, I will reply a message to the other party. Protocol unreachable. But usually, these unreachable packets cannot be received. Because now for many devices, by default, the error message reply of ICMP will be turned off. But, in case the network goes down one day, according to these error codes you can to do a corresponding investigation. Port at the top. I can access the TCP protocol now. Suppose I now access the other party's port 80. For example, my local port is 1027. A local port greater than 1024. Random access to port 80 of the other party. The TCP protocol of the other party is indeed open. But the HTTP web service is not open. Port unreachable. So from network to host, to agreement, to port, layer by layer, is more and more detailed. But usually, UDP and TCP protocols are unreachable and very difficult to catch. Because for these public agreements, it is installed on the default network card. Generally, it is not easy to close. So I can't catch this thing. In addition, we will disable replying to this error message. What does it mean? Let me give you an example. This is a PC. There is a router on the public network in the middle. Assume that this is the peer router that the PC wants to access. Connect with each other. Now it is hoped that from the sender to access the peer. Generally speaking, there will be some corresponding strategies here. That is to protect. For example, the address of this server is 2.2.2.2. This address is 1.1.1.1. But in fact, now the server is not using the public network address. Private network. The export here is the server for NAT. The public network is also used internally. Now go to ping 2.2.2.2 from 1.1.1.1. For data. This device has routing. Data can come. But this device is not allowed to access. Logically speaking, it is to reply host unreachable. Or depending on the situation, may reply network unreachable. Can't access this device right now. Policies may have been made on this device. A call may be performed under the interface. When the data packet arrives here, it is intercepted. In theory, the router is obliged to reply with an unreachable message. But please be careful. If message reply, we are going to encapsulate the source IP of the third layer. The default encapsulation is the IP address of the outgoing interface. Now this interface replies to the PC with an unreachable. That is equivalent to exposing the interface IP as some more private servers. Now you know the IP address of the uplink device exit. Usually, I don't want this address to be revealed. So even if I do the strategy here, after the data arrives, it fails. Will not reply to unreachable messages. If the device replies with an unreachable message, will come out with IP. It is equivalent to leaking the IP of the current interface. Generally speaking, we will not reply packets to it. Everyone in future work. You can test devices from many manufacturers. Even if ICMP is unreachable for various reasons, you also don't get unreachable messages. It will not receive ICMP packets. There is a code value inside. Look at this type code, corresponding to this type and encoding. In theory, you will receive an ICMP message. But in many cases you can't receive. That is to say, whether the request timed out or was unreachable. It's not that you just have a network failure. The other party will definitely give you a reply packet. Depends on the other party. Is the service of replying data packets to you enabled? So there is no absolute. In many scenarios for safety, may not be able to reply. If this feature is enabled, can reply. Next, let's talk about the application of ICMP. ICMP has two major applications. The first one is ping. For ping. Actually, every time you send a ping, it sends an ICMP packet. Under normal conditions, you ping the peer on the device. We'll send 5 packets at a time. If I go to ping now, suppose the address on the right is this. The default is 5 packets. Then in these common parameters, only 2 are commonly used. One is called repeat. One is called source. Let's talk about this repeat first. Repeat means, how many do you want to send now? How many times do you want to ping? Let me demonstrate. For this router, I first look at the interface of the device. I have now configured an interface address on the device. Then I'll ping myself. Suppose I ping 192.168.1.254. It's sure to work. Let's see now. All we can see are 5 exclamation marks. That is, sending 5 is written here. Sent 5. Then you can specify it here. For example, I specify repeat here. Specify it only sends 1. If I give it 100, it sends 100. If we want it to ping all the time, let's say I let it ping 10,000. We will send 10,000. Press the Control key plus the number 6 key to terminate it. Otherwise it keeps pinging until 10,000. If you want to ping an address under Windows, how to ping it? For example, I'm pinging Google right now. Just enter A to ping it all the time. Let's look down. Have a source. I draw a picture to explain. When we talk about experiments in the future, we'll talk about the loopback interface, called loopback. When we do experiments and work on projects in the future, the source command is often used. A device on the left. A device on the right. Now the devices need to ping each other. There is a direct address between the two of them. Like how much? The one on the left is 1.1.1.1. The one on the right is 1.1.1.2. Because they are directly connected. So you can directly. But if on the left side this device here, loopback. For example, this loopback address is 2.2.2.2. The device on the left can directly ping 1.1.1.2. Because it defaults to this outgoing interface. To send messages. If the reply packet. The destination IP is the left device. The device on the right also knows how to get to the device on the left. The two of them can pass. That is, if no source is specified, it is the outbound interface. If source is specified, equivalent to now, it is from the address 2.2.2.2 of the left device. Go to the right device. Data can pass. Because when the data is sent, check the route on this device. But when replying to the packet, for the device on the right, it is not replying to 1.1. 1.1. It is replying to 2.2.2.2. It does not have the address of 2.2. Then it can't come back. Where are loopback addresses often used? Used to simulate a network segment behind this device. One of my devices on this device returns configured at 2.2.2.2. It is equivalent to connecting a device behind this device. This device is 2.2.2.2. Here is 2.2.2.1. I'm on this device with 2.2.2.2 as source. To ping this 1.1.1.2. Now the two network segments can communicate. That is, you can go directly to ping 1.1.1.2 now. You use 2.2.2.2 as source. It may not be possible to ping 1.1.1.2. If it doesn't have a route, it won't work. When we go to learn routing later, often originates from an address. To ping another address. To ensure that the routing configuration is correct. Less likely to be involved in NA. In NP, you will often come into contact with. Let's move on to the last thing. Traceroute. This can see what happened to the equipment along the way. There is also a source in traceroute that can be specified. There is nothing special to pay attention to. I will give you a simple demonstration. Still take PC as an example. I will give it a trace route first. Add a dir. Don't worry about this. I don't want it to go to domain name resolution. For example, I give it 4114. Let's test it. It is the same as ping. They are all encapsulated with ICMP packets. But you will find there are many symbols in the middle. We wait patiently. Usually use this command. You will find some places can go. Can't reach some places. That is to say, I will go to such an address in the future. Public network addresses along the way. We all know. The domain name resolution server is actually a public network service. I have now visited an address. This is a public address. Along the way, you have to go through a lot of devices. On the public network are public addresses. What I want to know is my PC accesses to the public network. Another time when the service was finally docked. Who are these devices in the middle? We will use traceroute. Here you will find there are a lot of things we can't catch. Many are symbols. For the current overall equipment, it will have a security feature. We now talk about its mechanism as a whole. Why it can track so many devices. I give an example. I draw a corresponding environment. I am drawing 5 routers now. Device 1 is 2.2.2.2. Go to access device 5. Device 5 is 1.1.1.1. When I visit, how does traceroute retrieve each device? This is called traceroute. It is based on the TTL and the entire IP packet is carried out. I said TTL when I talked about the message before. TTL is time to leave. Where does this message go? You can't forward it down. If a message is received now is 0. TTL value is 0. The packet will be discarded directly. Device 1 sends a message to 1.1.1.1. That is, from 2.2.2.2 to 1.1.1.1. First a message is sent. In this message, TTL is equal to 1. This proves that this message can be sent once below. Now after device 2 receives the message, the local will subtract 0 from this one. Becomes 0. Once this message becomes 0, it can no longer be sent down. It is equivalent to the termination of this message to device 2. Can't send it down anymore. So now device 2 will return a TTL timeout to the source. This means device 2 will use the address of this interface to reply to device 1. Device 1 receives the message and knows it is this interface. It knows who its next device interface is. Next we will send a new message. In the new message, TTL is equal to 2. The message is here. TTL minus 1 equal to 1. Can continue to send down. Post here. After receiving device 3. TTL minus 1 again. Minus 1. Reduced to 0. Once equal to 0 here. It proves that the data cannot be sent down. Now tell device 1. TTL timed out. The packet of device 1 did not arrive at 1.1.1.1. So device 3 will also use its interface. Send a message to device 1. Device 1 gets the address of device 3. Next, TTL is equal to 3. Arrived at device 4 here. Device 4 will now also reply with a packet to device 1. After device 1 gets the address of device 4. Then go on down to device 5. This is the destination. The message is also over. But device 5 will also reply to device 1. Device 1 knows that it has arrived. So it is equivalent to in this process. TTL keeps increasing. Cause the packet to arrive at a new device whenever. They all have to reply to device 1 with a timeout message. Then use this as a means. Get the IP address of each interface. So device 1 knows which device it has passed through. According to us, we should be able to get other equipment. Why do symbols exist? Because some equipment along the way is invisible. That is to say, a detection based on TTL value timeout may cause the address of the device to be exposed. That is, IP addresses of devices along the route will be exposed. Please pay attention. On our website, especially within operators, including possibly other public networks, many addresses that serve. It doesn't want you to know. Now you can see. It's all insignificant addresses. Those more important devices. And some important configuration addresses. You can't see. So these devices are forbidden to send ICMP-based TTL timeout packets. The TTL value is also one of the ICMP messages. Except that it uses the value different from what we just said. It is 11 and 0. You don't have to remember this. It is also the error message of ICMP reply. That for us. Some devices do not allow replies. You can't see it if it doesn't reply. But it will also help forward. Like the devices I just talked about. It can help forward along the way. That is, the PC has now sent a data post here. It doesn't reply to you. For example, TTL value is equal to 2. It doesn't reply. But send TTL value equal to 3. It helps you forward. Because you are now on the public internet. It is a public network device. You can't get its address. It can help you forward. But it doesn't message you back. Then what you see is the symbol. For example, This address allows you to reply. You can see. If you are not allowed to reply, what you see is the symbol, including some addresses you can't see. Okay. Some students will ask, what do these 3 symbols represent? It means that if the device sends 3 consecutive, if the TTL value is equal to 2, while other devices do not respond, then after sending 3 messages, the TTL value equal to 2 will no longer be sent all the time. It is time to send a TTL value equal to 3. Just skip it and move on. At last, ICMP has a problem with redirections. We just saw this in coding. That is, the message type. The TTL value timeout is also an ICMP message. It's just that it's 11. Here is 0. Here is an echo reply and echo request. When we send a ping, this ping packet is sent over. It's called echo request. The ping packet is sent back. It's called echo reply. Now let's talk about ICMP redirection. It is very simple. For us now, let's check the environment first. Host A's IP address is 10.0.0.1. Host A's gateway is 10.0.0.100. The internet is connected behind the gateway. If I want to go online in the future, my traffic goes like this. But you will find, now there is a server in the company. The server is 20.0.0.1. Host is 10.0.0.1. If the data is sent now, the host wants to access 20.0.0.1. Then in theory, the device is here. If people see it, the data should be transmitted like this, because the device is on the left. But for PC, it is on the 10.0.0.0.0 network segment. It is on the 20.0.0.0.0 network segment. If you access it across network segments, the host cannot directly find the server. Only gateway. But for the gateway, now the data is at the gateway. But the connection behind the gateway is the internet, dealing with the business of the operator. The internal server is here. Then the internet needs to help the server forward, because the server wants to access. The data has to be reset like this. That is to say, the data is transmitted like this. That actually, the data should go like this. It shouldn't come to the gateway. But since you configured a gateway, now across the network segment, gateway, so its contradiction appears. The gateway will now consider, if you visit now, better not to find the gateway, because the server is on the left side of the host. Just go to the left for the data. For the gateway, there will be a routing table. This routing table is premised. The routing table needs to know that the network segment 20 is passed in this way. To do a reitem, which is equivalent to, now the gateway discovers. After the data is passed, the gateway receives the message from the host through this interface. The gateway needs to help the host forward. You have to send the message through this interface again. For routers, if the future goes to the server, the next device to arrive should be here. Then the router will tell the host, if going to the address of 20.0.0.1, the next time the interface to this device is directly reached, the router sends a message to the host. Point out the direction of the host. But please note, just for such a destination IP to be accessed, to specify a direction. This is called ICMP redirection. That is, different network segments need to find a gateway. But the gateway received a message from this interface. It wants to help forward. Have to switch out from this interface. And for the gateway, Look at this interface. Since the data can be transferred from here, then here, then it means that the router can go directly to this. Also in the same paragraph. And it happens that there is also a route to it. But please be careful. It is only for one destination like this. To tell you next time, go straight to the left. Then if your future, for example, you visit an address 8.8.8.8, such cross-segment access. Should you go through the gateway? Go through the gateway. This is how the data traffic goes normally. Only when you send a data. When it still comes out of this mouth, it will send you a redirect. Tell you now the next device is going to the left. That is to go through this interface. Redirect this message inside. It will point you to this destination in the future. Next device, go this place. It will only go like this. When accessing the server. This is called ICMP redirection. Host and device are directly connected. It means that the interface of the router can directly send to the host. The host wants to forward to the next device. It must also be passed to the direct connection device. The three of them are still on the same network segment. So don't bother going astray. Just go straight away. This is the redirection. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.